So today's session will be on diving deep into algorithms, Naive Bayes and SVM. We have our two speakers, Sneha B, who is a major student, AI major student, and Dipshikha, who is also an at AI major student as well. Before starting this session, let me tell you that we are having the next session on 9th March 2022, same time. Hope you can also join at that time as well. Over to Sneha and Dipshikha.
All right. Hey everyone, and thank you so much, Hema, for that wonderful introduction. So I'll be sharing my screen real quick. So let me know if my screen is visible.
Yes, it is.
All right, great. Okay then, so let's get started. Thank you all so much for being here today and really excited to present this session for you guys. All right, so what are we going to do today? First, we'll have a small recap, and then we'll be talking about Naive Bayes, SVM, their applications, and then we'll look at some general differences between SVM and Naive Bayes. And finally, we'll be going to a coding session. So a recap of what we did last time. In the previous session, we basically spoke about regression and classification. So what is regression essentially? Regression is simply predicting a numerical value from some given data. And classification is basically, defining a particular object as part of one or more different classes. And for regression and classification, there are many different algorithms. So we mainly discussed for regression, the linear regression algorithm, and for classification, logistic regression. So linear regression works in the format of fitting a line to some data, and logistic regression has an S-curve with a threshold. So if it's above the threshold, it puts it as 1, or it's below the threshold as 0. So logistic regression works with classes, and linear regression works with numeric data. Now, in today's session, we'll be talking about two new supervised machine learning algorithms that work very well for classification, and SVM also works for regression. So yeah, that's what we'll be talking about today. And we'll first start off with Naive Bayes. So before I get started, let's have a small experiment. Now I'll give you some details. You'll have to predict the final outcome. So now there are two balls. There's football and a basketball. Now you'll have to predict based on the data I'm giving you whether the ball I'm thinking of is a football or a basketball. So this particular ball has white and is colored white and black. It has pentagons and it has lines on it. So when you think of all of this, it is white and black, has pentagons and lines on it. What is the ball that comes to your mind? All right, Shaw has put in football. Soccer, yep, Stacy, that's nice. Soccer, so Jessica also says that. Great, Sunil, Akansha. All right. So there's someone who says volleyball, but the classification is only between football and basketball. And most of you said football. So that's absolutely right. So what I just explained to you, that is essentially the essence of the Naive Bayes algorithm. Sorry, just a second. So the Naive Bayes algorithm works in this manner. You have certain features. What are these features? Features are something that help you describe the final outcome. So what did I just say to all of you? I said it is white and black, it has pentagons, and it has lines. So these are features or characteristics of a football, right? So that's what features essentially mean. And these features are independent from one another. What do I mean by that? That means that they have no, just because it's white and black, it doesn't necessarily have to mean that it has pentagons. Just because it has pentagons, it doesn't necessarily mean that it has to be white and black, or it doesn't necessarily mean that it has to have lines. So each of these features are totally independent from one another. Just because one exists, it doesn't mean that the other has to exist, or the other doesn't have to exist. So that's what I mean by these features are independent from one another. And what do? We try to take equal probability of all these features. So I give you 3 features, and all of you, when you decided to tell me the answer of whether it's a football or a basketball, you took all of those 3 features into account. You didn't say, okay, it's white and black, and So if I said white and black, did you completely omit this? No, you also included this feature. You also included this feature. You also included this feature. You included all of these three features before you gave me the answer of it being football. So that's what naive Bayes does. Any machine learning algorithm, supervised machine learning algorithm, you always have a set of features and a target variable that you have to predict. So those features help you identify the target variable. Now, naive Bayes assumes that these features are independent from one another. That is, they have no dependency amongst each other. Also assumes that they are equally probable or they have equal probability on the final outcome. It doesn't omit one just because the other exists. So that's what I mean. That essentially is what naive Bayes does. So if you didn't understand this, let's maybe try to clarify it with another example. So now I'm going to tell you that you have to classify if this particular thing is an apple or not. So I'm going to tell you, and again, I'm going to tell you three things. So one is that this has a sweet taste, it is round, and it's red in color. So what comes to your mind? Is it an apple or is it not an apple? It has a sweet taste. It's round and it's red. It could be an apple. It could also be a cherry. So this is quite, you never know what the answer could be here. So if you understand, in real life, features can't always be independent of one another. You can't just have these three features that are independent of one another, completely unrelated to predict a final outcome. So maybe just for this example, let us assume that a sweet tasting fruit that is round and red in color is an apple. So why am I asking you to assume this? Because this is what naive Bayes does. It takes in certain independent features. So that's what I said. That was sweet, round, and it's red in color. So these are three independent features. And we take these three as equally accountable. So let's maybe exclude the possibility of cherry for right now. We can come back to why naive Bayes doesn't work. See, many of you guessed cherry. So this is a clear indication that naive Bayes might not always work, because you can't always assume that features are independent from one another. So we'll again come back to this when we're discussing the disadvantages of naive Bayes. For now, let's just assume that this round fruit that's sweet and red is also an apple. So when I say it's sweet, it's round, and it's red in color, we see that these three features are independent of one another. Just because one exists doesn't mean the other should exist or should not exist. And it has equal accountability for the final outcome. So that is what a naive Bayes algorithm does. This is essentially what we learned in both of these examples, the football example as well as this apple example. This is what naive Bayes algorithm does. It uses probability and it tries to predict based on certain information if this particular new object falls into this class or not. So naive Bayes actually has a lot of math involved. And to understand the math behind it, you need to know concepts of probability, such as conditional probability and things like that. So since there are a lot of newcomers, I will not be diving deep into that. I'll just mention the formulae. But if you're interested, you could always ping me later and we could have a discussion on the same. All right. So naive Bayes algorithm, what exactly is it? So naive Bayes, the main job of this naive Bayes algorithm is to take historical data. What do I mean by historical data? It was the data I already gave you. So before in the football example, I said it's black and white. It has pentagons, it has lines. So that is historical data, data that everybody already knows. And based on this data, you will draw out some probabilities. You will draw out some probabilities to decide which a class of outcome does it fall under. So one thing to note is that naive Bayes only works for classification. So like I mentioned, based on the particular features that you have, or based on the historical data that you have, that is the information you already know, you got to get probabilities. And these probabilities will help you in determining which class that particular object falls under. So it takes historical data, that is knowledge about previously occurring events, and it generates a table of probabilities. So there is a lot of probability involved. Based on whatever data you're given to it, it generates a table of probabilities. All right. So this is what the naive Bayes algorithm essentially does. It's a generative model. Now that might seem like a new term to everyone. What is a generative model? So when you're learning about classification, like I mentioned, classification is simply taking an object and putting it into one or more classes. So that's all that classification does. So when you're talking about classification, there are two different types of models in classification. One could be a generative model, another could be a discriminative model. Now, naive Bayes actually falls under the generative model. What is this generative model? So generative model is one that always learns everything about its data before it can predict the particular class of the data. So what do I mean by this? So there's this very popular story that is used to explain generative and discriminative algorithms, and maybe I'll just take use of that. So there is a father who takes his kids to the zoo. Now he takes his kids to the zoo and he looks at two cages. There's a lion and there is an elephant. And he asks his two children to identify, if he points at one cage and he says, is this a lion? So what does one child do? One child looks at the lion, understands every single feature of the lion, then looks at the elephant, understands every single feature of the elephant. And then it says, oh, okay, so now I've understood every single possible thing about the lion, every possible thing about the elephant. And now I understand that the cage you're pointing at is definitely lion. Now, the other kid, what does it do? It just looks at the differences. Okay, so this elephant has a trunk, lion doesn't have a trunk. So it just looks at what differentiates an elephant and a lion. And based on simply these differences, it says that the cage that the father is pointing to is a lion. Now, these are two different ways of learning. So the first method that I said, that is learning everything about the lion and everything about the elephant, that is known as a generative model. So that's what we're doing with naive Bayes. We have historical data. That is the data that was already given to us, like we mentioned. So in the case of the apple example, the sweet, the color, the shape, and in case of the football example, white and black, the lines and all of that. So that is information that's already given to us. And based on this information that's already given to us, the generative model draws probabilities. It understands everything that it possibly can about the data. And based on that, when a new data comes, it classifies it as either one of the classes that's there. So like I mentioned, it's a supervised machine learning model. So you have a set of features. And like I said, these features are independent. And you have a target variable. So in the training phase, the target variable is also used to help training. And that's why it's called a supervised machine learning model, because we send in labeled data. Now it's based on something known as the Bayes theorem. So naive Bayes, why did the name naive and Bayes come up? So if you like, naive essentially means innocent. So why is it known as a naive algorithm? It's called so because, or naive can also be talked about as the, the base form or the very simple form. So it's called naive because it assumes that all the features that are given to it are independent. That is why it's known as naive. Now it's called naive Bayes because it's based on this particular probability formulae known as the Bayes algorithm. So everything that I was talking to you about right now, that is, you had prior data, and based on the prior data, you're trying to detect the outcome of the class. So based on the data given in the first example, we were able to predict whether it was a football or a basketball. So all of this can be formulated into a probability formula known as the Bayes theorem. Now, this does require a lot of probability knowledge and something about conditional probability. So I'll simply just mention the formulae in the next slide. So yeah, like I mentioned, the assumption we take are that there are independent features here. So no feature is dependent on the other. That's the assumption that we take. And there is always an equal importance of the features. So whatever features are there, we always give equal importance for these features in predicting the final outcome. So we don't always, like, just because one feature is there, we don't omit another feature. We don't do any such thing. They are independent from one another and they have equal accountability for the final outcome. So these are the two assumptions that the naive Bayes algorithm makes, which is why it is known as naive. So this is the Bayes algorithm. So I'll just not go into the details of it, but what we're trying to predict is that the probability of A being true given that B is true. So you can think of it in this way. The probability of the fact that the object in front of you is a football, given that it's black and white. It's something like that is what you're trying to predict. That's how you try predicting things with naive Bayes. And here you're just multiplying the different features that you have. So the other different independent features that you have in this scenario, that is what you're trying to multiply here. So this could get a little confusing if something known as conditional probability is unknown. So I'd encourage everyone to give this formula a read. And if you still have any doubts or want to know more about what this formula is and how it exactly works, you can definitely let me know. I can share a few links and also be up for a chat about the same. All right. So now we spoke about naive Bayes so far. Let's talk about where this naive algorithm is used. So one very prominent place it's used is document classification. What is document classification? So given a document, based on certain words that are present in the document, this naive Bayes algorithm will be able to predict which class it falls under. So if you take the use of this, look at this GIF, there is a receipt, there is a document, and there are 4 classes: invoices, receipts, passport, and pay slips that it must fall under. So based on the words that are there in this document, it is finally classified as a receipt. So that's how naive Bayes works here. Then the very, very popular use case of naive Bayes, the place where it works the best, is spam email classification. So in spam email classification, for an email to be identified as spam, there'll be certain words that basically, differentiate a spam email from a ham email. So naive Bayes uses those words as the independent features. And based on this, it is able to identify if a given email is spam or not. So that's about spam filtering, and it's very, very popularly used in this field. Then we have sentiment analysis. So we definitely did touch upon this when we were speaking about classification in the previous session. But again, sentiment analysis is where you have a sentence and you have to basically understand the tone of the sentence. So if you say this was remarkable means that it's good. So that's a positive. Or if I say this hotel was a nightmare is there. So that means it's a negative tone. Or it says, yeah, this movie was so, or it was okay. So that's like a neutral. You were not very happy, you weren't very sad either. So that is sentiment analysis. Again, just like in spam classification and in document classification, there are certain words here. So these words are again treated as the independent features for a naive Bayes algorithm. And based on this, it is able to classify whether it's positive, negative, or neutral. So that's about sentiment analysis. And finally, we have recommendation systems. So if you popularly use any e-commerce site like Amazon or things like that, when you go and purchase one thing, you'll always be recommended a few other things. So that is a recommendation system. It also works very well in platforms like Netflix, YouTube, and things like that. So if you can look at this GIF, there are two customers who basically viewed a mobile phone. Now the first customer also viewed headphones. So those headphones are recommended to the second customer. So there is an algorithm known as collaborative filtering. That algorithm, along with this naive Bayes algorithm, are used to build a recommendation system. So we learned about 4 applications. One is document classification, spam email classification, sentiment analysis, and also this recommendation system. So recommendation system, again, when you purchase a product or when you watch a particular genre of movie, TV show, or just a YouTube video, you'll always have the users who did this also did this. Users who watched this also watched this. So that's what's being shown in this GIF. And an algorithm known as collaborative filtering is used in conjunction with this naive Bayes, and together they help in building a recommendation system. So that's all from me. Now, I'll just take a few questions. Please share some links regarding the further explanation of naive Bayes. Yeah, sure. I'll make sure to put it up in the Slack channel. And does this assume a relationship between A and B? Can you make that clear, whoever asked this question?
Hi everyone. If you are having any questions regarding what Sneha has just spoke about, please ask the questions right now.
Oh, the formula I posted earlier. Okay. No, this does not assume that it has any relation. Okay, so I just mentioned a thing about probability. In probability, when you have something known, oh yeah, okay, that does not, so you're asking A/B. So this A/B is the conditional probability. Again, I won't go too much into it because I don't want to talk about the math as it may confuse attendees who are absolutely new to this concept. But this is something known as conditional probabilities, where you have this information that is given to you. So I'll take the simple example of the football again. Let's assume B is the information given to you. And in our case, B as the information given to you would be, in the case of the football example, that it's black and white. Now you have to predict A. So A in our case could be that you have to predict that it's a football. So in totality, you read it as you have to predict that it's a football, given that you have the you have black and white. You have the color of the ball is black and white. That's given to you. And you have to predict that it's a football. So this in no way means that you have any relation between these two. It's something known as conditional probability. There's no relation at all, absolutely. You're just given some previous information. Using that previous information, you have to predict the class. So that's what we've been doing so far. Even with the Apple example or the football example, we always had some previous information. And based on that previous information, we're trying to predict a new information. All right, so I'll continue typing out the answers for the rest of the questions in the interest of time. So over to Dipshikha, who will be taking over SVM. I'm so sorry, I just had this last part. So this was all about what are the advantages and disadvantages of naive Bayes. So advantages is that since there is independent features, that's why there is very fast training and testing that takes place here. And another thing is it's not sensitive to irrelevant features. Now, what happens in the case of, okay, let's say you have a data set and you have to predict, okay, let's go back to our very running example, that is this football example. Now, we also had, let's say, some irrelevant feature like age of a person. The age of a person totally does not, age of person is nowhere related to any of this. It cannot even help you in predicting whether it's a football or a basketball. That is completely unrelated to the problem we have at hand. So imagine the data set is black and white, has pentagons, has lines, age of the person, and is a football or a basketball. So this age of a person is irrelevant. And in some machine learning algorithms, when this age of a person is involved, that is an irrelevant feature is involved, it could affect your final outcome. But in naive Bayes, since it takes every feature independently, takes it as equally probable. So when it understands that the age of the person is irrelevant, it does not take its probability at all. So in that case, it's able to predict, even though there is an irrelevant feature, it is able to predict whether it's a football or a basketball. So those are the advantages. And then the disadvantages is that it has something known as zero frequency. So here in this formula, if you see, we're multiplying things. So let's say when you're trying to predict something or when you're trying to classify something, there is a new category, an absolutely new category given to you. In that case, that category has never been explored before. So the probability of that category will be zero. That means that the entire formula will amount to zero. And that might not always be the case. That will lead to wrong answers. So this is a problem known as zero frequency. Whenever there's a new category during training that has never been explored before, the probability of that will come to zero. And that might not be zero probability because it will definitely amount to some importance in the data. So this is one thing called zero frequency. Again, if you're not able to understand the zero frequency completely, that is fine. I will soon share some links about naive Bayes where you can understand the math also in a very easy way. So you can maybe watch those videos for whoever's interested and whoever knows something about probability. You can go ahead and watch those videos so you'll understand zero frequency better. But for now, just imagine that in the training phase, you came across a category that was never there before. So when you come across things like that, the probability will be zero. And if the probability is zero, the entire probability of that particular class becomes zero. And that can't always be the case. And like I was mentioning, so in the Apple example, many of you mentioned cherry. That's because there are so many features that can be dependent on one another, right? You can't always have these features that are independent. So if it's round and sweet, you could think of it as cherry as well. So in that case, there is no total independence in real life. There are many real life data sets that have some correlation or some dependency between one another. So that these are the disadvantages and advantages of naive Bayes. And yeah, that's all from my end. Over to Dipshikha.
Hi everyone. Can you hear me?
Yeah.
I'm really sorry that for some reason my webcam is not working. Really sorry for the inconvenience. So I'll be continuing. Thank you, Sneha, for that wonderful explanation of Naive Bayes. I'm pretty sure that all of the participants understood it really well. So I'll be starting off with support vector machines. Support vector machines, again, it's a supervised machine learning algorithm that is mainly used for performing classification and regression as well. So usually support vector machines are mostly used in classification problems where the data is sparse. That is, it's easy to classify and exists sparsely, where it's easily distinguishable, and thus it's easy to classify. So a basic thing what we do here is we perform the classification by finding the hyperplane that differentiates between the two classes. Now I'll be using a few terms while I explain SVM algorithm. There are four terms that I'll be using: support vectors, hyperplanes, margins, and kernels. So let me continue and I'll get to the definitions of the important terms in a while. So the basic premise behind how SVM works is quite simple actually. So given any data that is plotted on a plane, as you can see in the graph, given any data, this algorithm will create a line or a hyperplane to separate the data into different classes. So in the first graph, you can see there are a couple of data points that have been plotted, and the hyperplane or the straight line creates it distinguishes between two classes. So it's basically a linear SVM classifier, linear because it works in two dimensions. So linear SVM classifier works by drawing a straight line between two classes. So what data points belonging to one class fall on the one side of the hyperplane, and data points belonging to the other class fall on the other side of the hyperplane. This algorithm is also a discriminative model, as Sneha explained earlier, which means that basically given a new object, the model will find the difference between the object from the others based on the immediate properties of the object and not by studying the object thoroughly. So now I'll be explaining the important terms. The four important terms: support vectors first. So support vectors are basically the data points that are closest to the hyperplane that is mentioned. So in the graph, you can see there's a hyperplane drawn, and there are two data points that have that are marked here as support vectors. So these two data points are the points that are closest to the hyperplane. So these data points will define the separating line or the hyperplane by calculating margins. So we can see the line that is perpendicular on the hyperplane from the data points are known as margins. So margins are basically, it is the distance between the hyperplane and the nearest data point or the support vector from either side. So margin is basically the separation gap between the two lines, and it is calculated with our usual perpendicular distance from the line formula. And so the purpose of SVM is to maximize the separation gap or the margin. Now I'll be explaining what a hyperplane is, since I've been speaking a lot about hyperplane. Hyperplane is basically a decision boundary that separates a given set of data points having different class labels. So in the given graph, you can see that the hyperplane is clearly, separating the two two class data points, that is one belongs to the blue data points and the other class is the brown data points. So the hyperplane clearly distinguishes the two classes, and that is basically called a hyperplane. So the SVM separates the data points using a hyperplane with the maximum amount of margin. So we have to maximize the margin. Now, hyperplanes can be of different kinds depending upon the dimension of data you have. So if you have a two-dimensional data, you can plot it in an X and Y graph, in X and Y graph coordinates, and you'll get a linear line that is the hyperplane, a linear line that properly separates the data points according to their particular classes. Now, if we have, in an example where we have a data that the data points that are not clearly distinguishable. So in this graph, we can see that there's a brown data point, there's a blue data point, and there's a blue data point in the second column, and there's a brown data point. So there's no particular line that can, distinguish both the browns and the blues from each other. So in this case, what we do is we use a kernel. So a kernel is basically a mathematical function that is used to transform the linearly inseparable data. Like if it's in two dimension, you can't really separate the data properly. So what you do is we project it to a higher dimension where the data is properly separable, and we create a hyperplane here. So for a 3D, for the graph that is linearly inseparable, we transform it to a higher dimension and plot our hyperplane accordingly. So for a simple classification task, given two features, we can imagine the hyperplane. Can you go back? Yeah, thank you. We can imagine the hyperplane being a linear, that is a one-dimensional line separating the data. And given the second image, we can see that the plane that is present on a 3D surface that will be used to separate our data. So the goal of SVM is basically to identify an optimal hyperplane that separates the data points and maximizes the margin, that is the difference, that is the distance from the data points to the hyperplanes. So we need to maximize the margin to get our optimal hyperplane. You can go to the next slide.
Sorry, Dipshikha, before you move on, could you just explain the four terms again? And I'll be sure to highlight it on the diagram because I feel people have some doubts.
Sure. The four terms, sure. So yeah. So the four main terms are, the first one is support vectors. Now in the first graph, we can see that we have a couple of data points that have been plotted. The support vectors are the ones that are closest to the hyperplane that we need. The support vectors are the data points that are closest to the hyperplane. And these data points help us define the hyperplane. So let's consider these points to be the reference points that help us to plot our hyperplane. The second important term is a hyperplane that I've been talking about a lot. So hyperplane is basically a decision boundary. It's just a boundary, like in the 2D graph that you can see. The hyperplane distinguishes between the blue data points and the brown data points. So it's basically a boundary that separates one class from another. So like hyperplanes differ from dimension. So if you have a 2D data, like a 2D dimensional plane, your hyperplane would be a linear line. And in cases when you have linearly inseparable data, that's when you project the data, and then you get the hyperplane, which exists in 3D format. So your hyperplane basically depends on your data, what dimension you're plotting it on. The next important term is margin. So margin is basically the distance between the hyperplane, that is the boundary, and the nearest point, that is the support vector. So margin is basically the data from the margin is basically the distance between the support vector and the hyperplane. And so this is calculated using our normal distance formula, that is perpendicular distance between two lines. And we try to maximize this margin to get our hyperplane, maximize the margin from both the sides so that it's balanced on both the sides and our optimal hyperplane is obtained. The last important term is kernel. So kernel is basically a mathematical function that transforms linearly inseparable data into a higher dimension. So in this case, we can see the data is linearly inseparable. Like we can't draw any one boundary that will separate our data into blue data points and brown data points. So we need a mathematical function that will transform the 2D data, like the 2D data into 3D, so that it's like distinguishable, and you can properly plot a hyperplane that separates the two data classes, that is the brown data points and the blue data points. So common kernel functions include linear kernel functions, Gaussian, RBF. For now, we'll be talking about linear kernel functions, but if you're curious and you want to know more about kernel functions, you can always look it up. And also you can ping me up and we can talk about it. Is that clear? Like, are the different definitions clear?
I think we can move on for now.
Yeah, I'll just take one question from Shaw. In the diagram for kernel, how did the red data points get separated? Exactly. So kernel is basically a mathematical function, right? So that mathematical function is basically being used to transform the data. So the data previously exists in a two-dimensional space. And we use that particular mathematical function to convert our 2D space into a 3D space so that we can properly distinguish between the blue data points and the brown data points. I hope that answered your question. All right. So moving on. Yeah, so formulating a hyperplane. Now, while drawing a hyperplane, we'll get a lot of hyperplanes actually. Like, you don't just get one hyperplane, you get quite a number of hyperplanes. So how do we find which one is the optimal hyperplane? So one thing that you guys have to remember is that the purpose of the SVM algorithm is to maximize the margin, that is the distance between the hyperplane and the support vectors. So let's consider this graph. Now here we relate each of the data points to be feature vectors that are plotted on the graph, and each features are labeled labeled with a class of Y. So yeah, each class is labeled as +1 or -1. The green data points are labeled as -1, and the red data points are labeled as +1 because they lie on the either side. Like, the labeling again depends on the user. So here for this particular derivation, like for this particular formulation, we are taking it as -1 and +1. So the optimal hyperplane has an equation that has a line equation. So as you can see, the data point, the line that passes through the support vectors from the green data points is omega x plus b is equal to -1. Now this is also analogous to our normal equation of a line, that is y equal to mx plus c. Here class y is y can be negative or positive, like -1 or 1, and mx plus c is basically the equation of our line. So we have plotted and considered the classes and the values accordingly. So yeah, now we basically need to maximize the margin. How did this formula, that is maximizing of 2 by magnitude of omega, come? It's derived from the formula of calculating the distance, the distance between two parallel lines. That's again a lot of geometry and calculation, so we'll not go much deep into that. But just know that that particular formula, maximization of 2 by the absolute value of omega, is derived from the formula of calculating the distance between two parallel lines. Now, one thing is that when you look this formula up online, you'll also find a lot of places where this formula exists as the minimization of half into omega square. So, which is basically differentiating the inverse, the inverse of this formula. So after differentiating the inverse of this formula, we'll get the formula that is usually available online. The reason why I put the maximization of the margin is because there is this one point that we are constantly stressing on, is the maximization of the margin to get our hyperplane. So we need a wider margin in an optimal SVM model to ensure less overfitting and better classification. So the wider the boundary, the better the classification and the distinguishable classes. You can go to the next slide. Now let's talk about a few applications of SVM. The first application is facial recognition. So SVMs are used in facial recognition to classify parts of an image as face and separate them from the parts that are not. So let's say a face is scanned, and there are parts of face like eyebrows, eyes, nose, lips. So it recognizes and classifies the parts of the face, and like classifies them as the face and the others as not face. So that's how it recognizes your face. So the training data for facial recognition contains an image of n by n pixels, like whatever pixels we have. So the training data consists of an image where each pixel is of two classes. We can consider +1 for face and -1 for non-face. So this SVM then separates the features from each pixel of both the classes, that is face and non-face, and creates a boundary around the face on the basis of the highest score that is gotten for the face features and the non-face features. You can go to the next slide. Yeah, text categorization. So the next application of SVM is text categorization. So SVM is also commonly used in NLP for document, article, and general text classification. So our training data typically looks like a database of documents or text classified into different categories. So this is used to predict and automatically categorize our document and text into news articles like politics or sports or editorials. And then we have emails. The categorization emails will be spam or non-spam, and web pages also, like product based web pages or just like fun web pages. So all these so SVM can be usually used to classify all these documents and things containing text. So how does it do the classification is that it compares the words and the sentences from one document to the other, and it calculates a score and compares it with the given threshold. So based on the score of the given document, the SVM model classifies it as for example sports and editorial. So if with a particular threshold, the given document might be sports or editorial. You can go to the next slide. So talking about advantages and disadvantages of SVM, one of the reasons why we use SVM, like the main reasons why we use SVM, is because it can do classification and regression on both linear and non-linear data. The second reason is that it's effective for higher dimensional data. That is, I just now talked about kernel. So kernel helps us in, transforming linear data into higher dimensional data. And that is one of the main reasons why SVM is used, and it is an advantage of SVM. SVM algorithm is also effective in cases where the number of features is greater than the number of data points. The disadvantages of SVM is it is not for large data sets, because in large data sets we'll have a lot of many number of features and also a lot of data points to plot. So usually while going through the whole data set, if it's a large data set, it might take a lot of time to go through all the data points and plot them individually and then find the margins. So it's not time efficient. So SVM is not generally used for large data sets, and it has a low performance in data sets with more noise. More noise as in like more overlap. The target classes are overlapping, and thus we can't find the proper boundary that distinguishes both the classes. So that's two disadvantages of using SVM. You can go to the next slide. Okay, so now we're going to talk about Naive Bayes and SVM, like versus SVM. So Runjan will launch a poll right now, and you guys can take like a minute or two to go through the questions and answer the poll. So meanwhile, I'll answer this question. What is the difference between document classification and text categorization? The difference is not major, like both the cases deal with text. But in document classification, we are going through the whole text and classifying it, like for an example, if it's a newspaper article. So we are going through the whole text and comparing them and providing them a score based on which they can be classified as, from a sports column or an editorial column or a global news column. And text categorization is basically, let me take an example of what Sneha mentioned before, sentiment analysis. So text categorization is basically considering each word and classifying what, in case of sentiment analysis, classifying what emotion it depicts. that is negative, positive, or neutral. But there's no major difference between them. It's both related with words only. I hope that's answered your question. I mean, if anyone else, any of the panelists have anything to add, they can feel free to do so. If you guys have any other doubts, you can always feel free to ask in the Q&A section. We'll be happy to answer.
I think we can end the poll.
Okay, so we have the results of the poll, and let's go through it one by one. So the first question, features are independent of one another. Most of you, that is 81% of the participants, have answered naive Bayes, which is completely correct. And yeah, as Sneha mentioned earlier, the features in the naive Bayes problem are completely independent of one another when used. So the second question is, uses non-linear kernels, RBF and Gaussian. So as I mentioned earlier, kernels that exist in SVM exist in linear, non-linear, RBF and Gaussian. So 83% of the participants have answered this right. That's amazing. Third question is used for classification and regression. So 73% of the people have answered this SVM, which is correct. SVM is definitely used for classification and regression, but it's popularly used for classification. The fourth question is used only for classification. So 77% of the people have answered naive Bayes, which is correct. Naive Bayes is used only for classification. The fifth question is, it is a discriminative model. 69% of the people have answered SVM, which is completely correct. SVM is a discriminative model as it considers the object then and there instead of studying it thoroughly and, you know, doing a history checkup on that object. It just checks what classifies that object as one or the other. Sixth question is, it's a generative model. So 69%, again here, 69% of the people have answered it naive Bayes, which is completely correct. It is a generative model, that it studies the whole object thoroughly and then gives out the output. So yeah, main points of difference between SVM and naive Bayes is, SVM is a discriminative model and naive Bayes is a generative model. The second main point is, SVM is used for classification and regression. It's used for both, and naive Bayes is used just for classification. And the third main point of difference is, SVM uses nonlinear kernels like RBF and Gaussian, and naive Bayes and the features that are used in naive Bayes are independent of one another. So I think we're done with the theory here. Sneha next will walk you through the code. Like, there's a small implementation. Please stay with us. Over to you, Sneha.
Hi, yeah. So does anyone want a small break? The code will just take around 10 to 15 minutes. It's almost similar to what we did last time, with just the libraries that are changed. All right. So we'll give you, like, let's say a 2-minute break exactly. So yeah. Maybe Hema, you could share your timer like last time.
So there are two questions. I'll probably answer those. How can SVM be used for regression? So SVM can be used for regression. Like in the case of regression, another parameter is added, that is a margin of tolerance, which is again beyond the scope of this particular webinar, but you can always look it up, or you can ping me up so we can, have a chat about this. And the next question is, doesn't SVM use linear too, like hyperplanes? Yes, it does. So the linear hyperplane would be a straight line in a 2D case. A linear hyperplane would be a straight line, and the others are in other dimension. Like for 3D, it's a whole 3D plane. And yeah, that's it. So if you have any other questions, please drop it in.
All right, so I will quickly be walking you all over the code and then we can end for today. So I'll share my screen again. Just a second. Yeah. Is the screen visible?
Yes, Sneha.
All right. So the notebook for this has already been shared in the chat. I could also just share it again. Yeah, I've shared the link for the folder here again. And in that folder, there's a in that Women Code folder, there is another folder called Code Files and Datasets. And under session 3, you will find this notebook. So please go to this files place, save a copy in the drive. Click on this first before you make any changes here. So create your own copy of this particular this particular notebook, and then go ahead and change it. All right. So today we'll be doing Naive Bayes and SVM on just one data set, that is the iris data set. Now, what does this iris data set contain? It basically contains 4 features: sepal length, sepal width, petal length, and petal width. Based on these 4 features, you're asked to predict what type of flower it is. So these are flowers. So it could be iris versicolor, iris setosa, or iris virginica. And this is what a petal looks like, and this is what a sepal looks like. So you'll be given the length of the sepal, the width of the sepal, the length of the petal, the width of the petal. And based on those 4 features, you're supposed to predict one of these 3 categories. So as we always do, what we first do is we import all the libraries. Now the libraries we've used are quite similar to the ones we used in the previous session. We again have pandas, and the alias we use as PD. So again, pandas is a package for those who are new. It's a package that helps you in data manipulation. Then we have Cbond, and you can import this as SNS. So why we use this alias is that you can reference it by a shorter name later on in the code. So again, we have Cbond as SNS for plotting. And then for importing, so this is just an extra. We don't essentially need this. So I will also be showing you how you can do without this. But sklearn, the library where we store all the different machine learning algorithms, also in itself has some data sets. And iris data set is quite popular, and it's actually already present in the list of data sets that sklearn has. So you can import data sets here. Then the ML models that we'll be using are SVC, that is Support Vector Classifier, as well as the Gaussian naive Bayes. So naive Bayes has many examples, and the most common one that we use is Gaussian. So from sklearn.svm, we import this. So sklearn is the big package, svm is a smaller module. Similarly, sklearn.naive Bayes, so sklearn is the bigger package, naive Bayes is a submodule. Again, sklearn metrics, we import accuracy score. Since we're using classification, the most common and popular metric for classification is accuracy score. There are many other metrics which we'll be learning in, like, let's say the 6th session or so. Sorry, the 5th session. And then once that's done, we have this chain test split to split our data into test and train. And usually when we import large data sets, so the data set we're using today is very, very small. But when you use large data sets, or we do some operations that are not normal, we'll get some warnings. So to remove those warnings, we use this particular package, import warnings, and then we filter the warnings and we ignore them. So as usual, we have, so in the folder that I shared with you all, there is code that under session 3, there is the link to the data set, the iris data set. So you can use that link and you can copy it here. So it's already been done for you in this notebook. So we have the URL. Again, we remove the redundant data that is beyond this, and we only use the one that is necessary, that is this. And based on that, we're able to identify and read the CSV files that's contained in this particular URL. So we read the CSV file using pandas has a function known as read CSV. So from this URL, we read the CSV and we print the very first 5 rows. So we have ID, then we have sepal length, sepal width, petal length, petal width, and we have the species.
Sneha, so again, do you give a minute for the people to open the documents, or you can just go to the document and give them a tour where to open it?
Oh yeah, sure. Yeah, okay. All right, so this is what the link, I'll just paste it in the chat again. This is the link to the folder. Now, this is what you will see once you open this link. So click on code files plus data sets. This is currently session 3. And this is your iris data set, the URL for which has already been pasted here. So you don't have to use it. You can open it in case you want to look at how the data set is. This is the notebook that we're currently using. So once you open this notebook, so go to the same place. That, let me just repeat. Again, you're here, go to code files plus data set, go to session 3, and this is the notebook that we'll be using. So once you open this notebook, go to file and go to save a copy in drive. So once you click on the save a copy in drive, you will have your own copy of this notebook in your drive. So you can add extra comments, you can try new different commands, you can basically experiment around. It's like your own version of this notebook. So that's what for you to basically be able to make your own changes, it's better to always have a copy of the same in your drive. So click on this and then you can make all your changes, because to this notebook, if you make changes, it will not be reflected and you may lose those valuable information that you've already written. So I hope that's clear. And yeah, all right, I will be moving on. So yeah, so we first had the URL. We read the CSV file. So normally when it comes to data science, we always use CSV or comma separated value file. And from there, we read the top 5 and the bottom 5 data. Now, if you look at this ID is something that's quite useless. It's basically the same as this number here. So since it's quite useless, what I decided to do is I decided to drop it. So I have the df. So I basically read the CSV file in this variable known as df. Now, from this df, I am going to drop this. So it's just a simple command that says df.drop, and then it drops off this column called ID. So later on, when we type in info, we do not have the ID column at all. So you can see ID is completely removed from everywhere. And when we type in columns later as well, ID isn't there. So from the entire data set, we've removed this column because that was totally unnecessary for us. All right. So what we did, we took a URL, we used the read CSV file to read it, printed the first 5 and the last 5 elements. And now we're going to print in info. So we're going to basically print in some information about this data set. So what is this information? So this information is basically the different columns that we have, that is sepal length, sepal width, petal length, and petal width. And then we're typing out how many values are there and how many of those values are non-null. That is, they must not be empty or missing. So each of these columns have 150 non-null examples. So you can see that here. That means that these are non-null. Non-null meaning they are filled, they are not empty. And you can see the data type. So the first 4 columns are float and the last one is an object because it's a class, it's a string. Then we basically again have a statistical description. So like I mentioned last time, you have all your features here. You can see the count. You can see all the different common statistical things such as mean, standard deviation, the quartiles, the minimum, the maximum, and everything. Then you have shape. So these are the number of rows. That is 150 rows that you have, and there are 5 columns. So 4 features plus the target column, that is species. And again, you're trying to check if there are any missing values, because once there are missing values, you will have to do some changes because your data machine learning model cannot deal with missing values. So you're checking if there are any missing values, and luckily for us, there are none. So there are no missing values here. And finally, just to check to see what the columns are, I've typed of df.columns again. So you can see there's sepal length, sepal width, petal length, and petal width, and species. So this is basic general things that we even did in the previous session, data manipulation, how we can view the data and things like that. Now, there is also a different method for you to load it. I'll not be running these 2 cells. You can run them on your own once you've created a copy of the same in your drive. So I'll repeat that. Go here, click on save a copy in drive, and then you can uncomment these cells and run it again. So iris dataset is already present in the sklearn dataset. So we imported this library. So from sklearn, which is the larger library, we imported something known as datasets. So iris dataset is already present here. And we basically, what we did here is that we gave a small description of the iris dataset. We printed a description. So the description will look something like this, but not in a neat format like this. It's, you can say, a combination of info plus description. That's what it will do here. And then we again did the same thing as we converted it to a data frame. So this is a data set. We converted it to a data frame. So it looks like this. And then we printed the first 5 elements. So I won't go too much into this. It's basically that you took it from the sklearn dataset rather than taking a CSV file on your own directly. So if you do want to give it a try, go ahead. So yeah, I've explained what these lines do. So this one loads the dataset. This prints a description. This converts it to a data frame that is in this format, so it's easier for you to read. And this prints the first 5 elements. So that was about data pre-processing. We did pretty much the same steps in the previous session as well. Now, just one plot for data visualization. Sorry, just a second. So we have just one plot for data visualization, and that plot is a heat map. So like I mentioned, what does a heat map do? A heat map looks at all the features that you have, and it tries to find out how correlated they are, how much dependency do they have amongst one another. Because if there's a lot of dependency, it's better for us to remove a column. So that way we don't have a lot of complexity. Now there are just 4 columns here. So it's okay if we don't remove a column also, that is fine. But if we were to remove one, you can see that sepal width is heavily. So if you look at the scale, the bright, very bright means a positive correlation. That is, if one increases, the other will also increase. Very dark means a negative correlation. That is, one decreases, the other will also decrease. So in this case, you can see that so obviously in the middle, that is the diagonal, since it's the same column, that will be the brightest. But if you can see otherwise, this sepal width has a very negative correlation with petal length and petal width. So that you can see here again, sepal width has a very negative correlation with petal length and petal width. So if we were to remove a column from this data set, we would definitely remove sepal width. But we have not removed that for our purpose. But if you were to try it on your own, maybe I'd encourage you all to try removing the sepal width centimeter column and then try running the machine learning models again to see how well it performs. So that's about a heat map, very, very commonly used plot in data science. Now, the next important step is that we split it into test and train sets. So we have our our train set. What will our train set have? Our train set will basically have all the features, every single feature except for the target column. So like I mentioned last time as well, any data you have will be split into three: test, validation, and train. But for our purpose, we only split it into test and train. So test will be, so train will be able to train your model, like, that is like teach your model. How will you understand the patterns that are given to you in the data? Test will be able to, it's like a final exam. It will be able to assess how well your model has learned the underlying patterns in that data. So for training, we take all the columns, that is, we take in sepal length, sepal width, petal length, and petal width, excluding the species, because species is something we have to predict. So that is what we take in X, and Y is our target variable. So we take in species. Then we use again the test, train test split as we did last time. We take X train, X test, Y train, and Y test. We split it in this manner. And we have X and Y. So X was all of our features and Y is our final outcome. And we give a test size as 25% and a random state 0. So that it's always the test and train split starts at that particular point and it doesn't vary to other places. That's why we always given a random state. You can think of this as a seed of sorts, where your split will always start from the same point again and again. All right, so this was the general things that we even did in the previous session. So if people missed the previous session, it'd be great if you could go through the recording of the same, so you also understand in a deeper manner what all of these steps are. Now about SVM. So here we had imported two models. We had taken scalar, which is the larger package, submodule of which was SVM. And from there, we'd imported the SVC function. So from that library, we imported the SVC function, and that's what we're doing here. So model, what we're doing is we're creating an instance of the SVC function. So we just want that SVC classifier, that is a support vector classifier. We just want to use that particular classifier to classify our points. So we're creating an instance of that and storing it in this variable called model. Now, what is our immediate next step always? Is that we must train our data. So to train our data, we have a bunch of features and the corresponding target variable. So since this is a supervised machine learning algorithm, we always given labeled data sets. So from these labeled data sets, what will happen is that when it's training, given the features, it will try to predict the final outcome and it will check if it's correct or not. So on its own, it will understand that based on these features, this final outcome is predicted. So the features are sepal length, sepal width, petal length, and petal width. And the outcome is a particular class of the iris flower. So in the training phase, it uses these four features to understand and find a pattern in the data. And based on the pattern that it finds, it tries to predict the final outcome. So to train any model, any machine learning model, we use the command fit. So using fit, we give X train and Y train. So X train was the feature, Y train was the outcome, and this will take up, so like we said, test size is only 25%. So yeah, this was about the training phase. Now, once we're done with the training phase, the next thing we move on to is the testing phase. So now training, we've taught the model. How does it have to perform? So 85% of the data was used in that manner. So, sorry, just a second. Okay. Now, we need to use 25% of the data. 75% of the data was used to figure out training. That is, we had features. From those features, we had to find some pattern. And based on that pattern, it had to learn and understand what outcome it has to predict. Now, for testing. So now that the model has learned everything, we give it a new data point. And this new data point, it has to find out which class does it belong to. So that is testing. So we given the test data set that formed 25% of our data. So we given this test data set, and this test we given, and the model predicts whatever it can. So it learned so far. So based on whatever it learns, it predicts some things. And then we find out the accuracy score. The accuracy score is basically a tally of how well your model predicted the correct class. So it checks how many correct predictions it made, and it gives you a percentage of that. So to check how many correct predictions it made, you need the actual outcomes. So the actual outcomes are stored in Y test. And what your model predicted for the same is stored in Y pred. So we make a tally of this. And we see that the accuracy of SVM is giving 97%. So that's about SVM. Now we do the exact same things for naive Bayes. So again,
Yes,
we create
yeah. Can you, so Rupal has asked that, can you explain the matrix one more time? How that can be a use?
this heat map.
Rupal, is this the heat map that you are asking of?
Rupal, you can just type yes or no in the chat.
Okay, so
Yeah,
I guess we can move on. Then after that, we can come back to the heat map.
Yeah, okay. I'll just quickly finish naive Bayes and come back here.
Yeah.
So we learned about SVM. Now we do the exact same thing for naive Bayes. So we again take in, so we already split it into train and test here. So we use the same split here as well. And then what happens is that we fit it. And once we fit it, we basically get the, we have an instance of the model, which is the Gaussian naive Bayes model. And then we fit the training data, that is the features and the outcome. And based on the features, the model understands the pattern and it's able to predict the outcome. And then we have prediction. So the model takes in the test data, that is completely unseen data. This X test is data that is unseen to the model. It takes in this X test, and based on whatever it has learned, whatever pattern it has identified, it's able to predict something. And similarly, we find the accuracy score. Now, in an ideal case, you would never get an accuracy score of 100%. But since this data is quite small and there are no errors or missing values here, we get 100%. Now, this is not always the correct answer. So if you remember from what we learned in our first session, this is actually a case of overfitting because the data is so small and it has absolutely no incorrect or missing values. That is why it is able to understand and learn everything there perfectly, and it's able to predict everything perfectly. So that's why it's able to work so well. Now, if we were to use the same Gaussian naive Bayes model to much more similar type of iris data, it will not perform very well. So that's why it's called overfitting, because in real scenarios or when it's put in production, it will not actually perform very well. So this is a case of overfitting mainly caused due to the data that we have. The data we have is very, very small and it's very clean as well. There is no inconsistencies. There are no missing values. So because of all this, it's giving you 100% accuracy, but that is not correct. So when you get 100% accuracy, always try to retrace back. And even when I got this, I thought maybe if I try to make a validation data set, that could maybe help me. So I tried making another validation data set and then doing it. But that also didn't help me. And then I realized that the problem was with the data. Because the data was so small and super clean, that is why it was able to perfectly understand the pattern of what was there in the data. So this is a case of overfit. So I just wanted to show you what overfitting looks like here. All right. Now to answer Rupal's question. A heat map is very, very important in data science. Why is it important in data science? Because a heat map is used to find the correlation between different features. Now, if two features are correlated, either positively or negatively, what do I mean by correlation is that if the values of one feature increases, the values of another feature will also increase. Or if the values of one feature decreases, the values of another feature will also decrease. It could be the ulta also. It could be that if the values of one feature increases, the values of the other feature decreases. So positive correlation is if the values of one feature increases, the values of another feature also increases. Or if the values of one feature decreases, values of another feature also decreases. That is positive correlation, as in the same things happen. It moves up together or moves down together. Negative correlation is that if the values of one feature increases, the other feature decreases. Or if the value of one feature increases, another feature decreases. So it doesn't move together. It moves in different manners. So that is positive and negative correlation. Now, what is the problem with correlation? Why can't we have correlation in our data set? because it makes one feature way too dependent on the other. And that causes a lot of problems, a lot of complexities. Of course, it's not in Naive Bayes always assumes that every feature is completely independent. That is not possible. But we can't have too much dependency either, because that would make it very complicated for any machine learning problem. Even previously, when we were doing linear regression and logistic regression, we did not want a lot of dependency between the features given. So usually when we find a lot of dependency, what we do is that we remove the column that is very dependent on its other columns. So in our case, you can see that sepal width centimeter is highly dependent or negatively correlated with petal width and petal length. So you can see here again, so sepal width, petal length, petal width has very dark region. So if you look at it this way also, you can see that sepal length, and petal width has dark region. So if you want to make your model better, what you can try to do is you can try to remove the sepal length centimeter and then try running your code again. So maybe that could help with your accuracy, that could help with your predictions and everything like that. So that's it about the code. It was, as you can see, it's quite similar to what we did previously. It's only the model that has changed. So that is how it's going to be for the subsequent sessions as well. The model and maybe the data set that we use will change, but everything else will remain almost the same, because in data science as well, these are the steps that are followed for you to learn and understand some data. So that's all from my end.
Hi everyone, if you are having any questions, any doubts, please feel free to ask our panelists.
I will stop sharing my screen. And I think a few people are already typing the answers to some questions. So.
Yes.
Okay, I think Heidi has basically given us some more information on Seaborn. So those who are interested, you can check out the Geeks for Geeks links that she has put in. I think that would be very useful. Thank you so much, Heidi.
Sonal, you can find the previous recordings in the link that will be provided now.
Okay, so
yeah, I will be sharing the link.
Yeah, sorry. So Erica's asked, what would you do next to make Naive Bayes work? So what I would try to do is I would try to take maybe incorrect data that has some inconsistencies. So in that case, what I can do is I can, if suppose the data has some missing values, suppose the data has like some incorrect values, I can fill in a few values in that case. And so I'll have some dirty data that I've cleaned on my own. And based on that, the data will not be very perfect. But so when the data is not very perfect, the model will not be able to perfectly draw a line. It will be able to draw an average line that will be able to, that will have some incorrect answers, but it will be able to definitely differentiate between the correct and incorrect points. So that's what I would do in that case. And that would maybe help me get a better accuracy, a more, accurate one, like more relatable one, not one that is 100%, because 100% is never correct. Okay, how are they calculated? So Rupal asks about the follow-up to heat map, the black regions, how are they calculated under the hood? So this again is a lot of math. So there's something known as correlation there's something known as covariance correlation in actually statistical concepts in mathematics. So you can Google up the formula for the same, or we can you can ping me later so we can talk about that. But there's an actual formula for the same. And it depends on like your standard deviation, your mean, and things like that. So this is how it's calculated under the hood. It's a mathematical formula. So I hope that answered your question, Rupal. Any other? Okay, so Marisol has tried removing the sepal with centimeter column, and Naive Bayes gets a 97% accuracy. So that's amazing. Thank you for trying that out. And will you be able to share the code for the same in the ML study group channel? Marisol, you can just put a thumbs up or a thumbs down, or if you're uncomfortable, that's cool too. Okay, so someone asks, how should I decide feature should be dropped? Highly dependent means 0.9. We drop feature more than 0.9 or negative 0. So see, if there is some dependency, you can, that's why you always plot a heat map, because heat map gives you in terms of colors. So when you see that it's extremely dark, that means it's towards the very low end of the scale. That means that there is too much dependency. If it's like light purple or very like, it's slightly dark or slightly light, you can maybe look, I'll just share that again so that you can, I'll let you know what I'm saying. So you can see these, this is fine. This is not a lot of correlation. That is okay. But this is way too dark. It's towards the lower end of the scale. So in that case, or if it's like this, way too light, if this was the color for some other columns, then you would have to remove that particular column because it's highly positively correlated. And here we can see that's way too dark. So it's highly negatively correlated. So whenever that's why plotting a heat map for this is good, because you can always see the variation in colors, and based on that, you can put, you can decide which column you have to drop. So you can either drop one that is towards the higher end of the scale or towards the lower end of the scale. So that's how I would basically drop the columns in my, in basically my data set. All right. Any other questions? If not, you can feel free to leave the session. Thank you all so much for sticking until the very end. And yep, that's all from our end.
We have one last question.
Why would you drop a column on the lower end of the scale? Because when it's on the lower end of the scale, that means that they have a negative correlation. That is, when one increases, the other decreases, or vice versa. And because, so either it could be a positive correlation or a negative correlation. No matter the case, they are correlated, highly correlated. That means they are highly dependent on one another. When they are highly dependent on one another, it means that the complexity of the machine learning model will increase. That is why I would drop things that are there on the positive end or the negative end of the scale. Hope that answered your question.
Hey Laila, answering to your question, yes, it's always good to have the understanding of the relative data. If you are having any more questions, you can reach out to Sneha or Dipshikha directly.
I think Hema, you answered Leila's question. In some cases, it's good to have domain knowledge, but yeah, that is correct. You're right. So these are just very basic and data sets that, any person who's very new to data science, these are the data sets that they will use and come across. We use Titanic, now we're using Iris. These are very, very popular ones. You don't really need a lot of domain knowledge for that. But yeah, when you go into larger projects, it's very, very useful to know more about the domain. So you'll understand what features help you and what features don't. Okay.
Yeah, I guess we can.
Yeah, even positively correlated ones are dropped. Shaw, I think Shaw asked the final question. So yeah, even positively correlated ones are dropped, and the negatively correlated ones are dropped as well. So you can see that the lightest color is always between the two variables that are exactly the same. Sorry, two features that are exactly the same. So when there is that same type of shade with columns that are not the same, then we drop that. So yeah, positively as well as negatively correlated columns, we usually try to drop one of the two or one of the three, so that you don't have that dependency and you reduce the complexity. So like Marisol did, she dropped the sepal width and she actually got a better accuracy and a more coherent or more accurate accuracy. That makes no sense, but you understand what I'm saying, right? It like in machine learning, that would be the right answer, because 100% would be incorrect. So yeah. All right, we're done for today. Thank you again all so much for joining us. And if you have any questions after this, please do ask it out in our ML study group. And like I mentioned, I'll be sharing some links for Naive Bayes. I'll share some good videos that help me learn. And if you guys want any more links in any other fields, you can always share it there. And I think someone had shared a Geeks for Geeks links about heat maps and Seaborn. So it'd be really great if you could share that on the Python and the data science Slack channels, the ML study group Slack channel. So yeah, that's all from our end. I think we can end the session. Thank you so much.
Thanks everyone for joining. Thank you, Dipshikha and Sneha, for this amazing session. Looking forward for everyone to join our next event, which is on 9th of March.
We'd love to
Bye,
see you all.
everyone.
Thank you.